All right, hello everybody, and welcome to this explainer. Okay, let's just dive straight into this incredibly powerful concept we're looking at today. We are exploring a method that I absolutely love. I call it the time traveler strategy for your Cambridge physics exams. Now, we are going to be specifically zeroing in on syllabus code 0625, but listen, whether you are sitting for 0625 or perhaps the 0651, 0652, the O-level 5054, or even looking ahead to the A-level 9702, the core framework we are talking about today is universally applicable. We're looking at the fascinating and often misunderstood topic of objects in orbit. Now, I want you to imagine for a second that you possess a literal superpower. What if you could walk into that exam hall, sit down, and literally see your completed, perfectly scored exam paper sitting right there on your desk before the timer even starts? Seriously, think about that. What if you could work backwards from that guaranteed success, rather than just nervously guessing your way forward through the paper? Well, that is exactly what we are going to do today. We aren't just going to sit here and read textbook facts. You can do that on your own time. Instead, we are going to reverse engineer the examiner's mind. We're going to completely transform how you approach this topic, moving you away from frantic last-minute memorization and stepping directly into the shoes of a top-tier, A-star Cambridge candidate. By the end of this explainer, you are going to know exactly how to structure your answers so that you are practically forcing the examiner to give you full marks. Sounds good? Let's get into it. So here is our game plan for today. We'll kick things off with the orbit challenge. Then we'll break down the 4-step blueprint and move into translating the physics. After that, we'll hit some real-life applications, put on our exam lens, and finally wrap up with final memory prompts. All right, section 1, the orbit challenge. Let's look at why this topic is actually a massive gateway for your physics knowledge. You know, when most students see the chapter titled The Earth in Space or Objects in Orbit, they kind of treat it like a decorative fact. They think it's just about memorizing. Okay, the moon goes around the Earth goes around the sun, got it, moving on. But in Cambridge physics, this topic is actually a micro gateway into a much, much bigger scientific pattern. It involves forces, motion, gravitational fields. It's a highly practical, rigorously tested area. I want you to genuinely ask yourself right now, what physical effect, measurement, or prediction actually depends on understanding this stuff? If we didn't understand the exact physics of orbital motion, what would actually fall apart in our modern world? Well, for starters, we absolutely wouldn't have GPS to navigate our cars. We wouldn't be able to predict global weather patterns or track devastating hurricanes before they hit the coast. We wouldn't have global telecommunications, satellite television, or international banking syncs. Understanding this topic isn't just about passing a test, right? It's literally about understanding the invisible infrastructure of the 21st century. When you take this application-first mindset into the exam hall, you become far less dependent on memorizing specific textbook phrasing, and you become so much more capable of reasoning your way through complex, unfamiliar, structured questions. You start to see the actual physical effects, not just words on a page. To really see how this plays out, let's compare two extremely common traps I see in the exam hall all the time. Imagine a dynamic split screen right now. On the left, we have a student named Alex. Now, Alex has studied hard. Honestly, maybe too hard. When Alex gets a question about orbital motion, they just overload the page with every raw physics fact they can possibly remember. They're writing about mass, weight, gravity, planets, stars, speed, just a massive brain dump. But here's the problem. There is absolutely zero analysis. There's no structure. And unfortunately, the examiner is just going to take their red pen and cross most of it out because it simply doesn't answer the specific command word in the prompt. It's a huge waste of time and mark potential. Then, on the right side, we have Sam. Now, Sam is actively panicking about the ticking clock. Sam rushes through the question, spots the word orbit, and hastily scribbles down a single formula without explaining any of the core relationships. Sam completely misses the specific command words like describe or explain. They are leaving so many easy marks on the table just because they rushed. Both of these approaches are deeply flawed because they totally ignore the assessment objectives. Alex lacks focus, and Sam lacks depth. We need to find the sweet spot in the middle. And before we reveal the exact blueprint that fixes Alex and Sam's mistakes, I need you to do something. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's look at the actual solution. Moving into section 2, the 4-step blueprint. This is where we learn how to perfectly structure your answers. Okay, so this blueprint right here, this is the core framework that transforms an average rambling answer into a top-tier, precision-guided Cambridge exam response. We are going to take the sheer chaos of a blank answer line and apply a rigorous structure that examiners absolutely love to see. It is essentially an adaptation of the Peel framework. You might have heard of it in other subjects: point, evidence, explanation, link. But we've designed it specifically for Cambridge physics. By breaking down your reasoning into these 4 distinct layers, you literally make it impossible for the examiner to dock marks. Let's break it down. Step 1. Identify the quantity or phenomenon. This is your point. What exactly are we talking about here? Are we talking about centripetal force, orbital speed, gravitational field strength? Don't be vague. Name it clearly right out of the gate. Step 2. State the relationship involved. This is your evidence. How do these quantities actually interact with one another? For example, you would explicitly state that as the orbital radius increases, the orbital speed decreases. You're showing them you know how the pieces move. Step 3. Explain the underlying physics. This is your explanation. Why does that relationship even exist in the first place? You'd explain that it's because the gravitational force is providing the necessary centripetal force, and that gravitational force inherently weakens with distance. And finally, step 4. Connect to real life or a specific observation. This is your link. You tie everything back to the specific context of the question. For instance, linking it to a communication satellite maintaining a geostationary orbit. If you force yourself to follow these 4 steps, Peel, you will never write a messy, rambling, or rushed answer again. It's a total game changer. Section 3. Translating the physics. Let's talk about the specific vocabulary you need to be using. Look, knowing the concepts in your head is really only half the battle. The other half is actually communicating them in the specific dialect of a Cambridge examiner. So often, I see students who understand a concept perfectly well, but when they go to write it down, they use everyday colloquial language. And everyday language is a massive trap because it's vague and relies on isolated facts. For example, a student might write, "The Earth pulls the moon, so it goes in a circle." Okay, well, technically that's not completely wrong. It is incredibly weak for an exam. It completely lacks depth. It's an isolated fact. Now, contrast that with precise physics vocabulary, which relies on clear, unbreakable cause and effect chains. A top-tier student, using our framework, writes this instead. The gravitational field of the Earth exerts an attractive force on the moon. This force acts perpendicular to the moon's velocity, providing the centripetal force required to maintain continuous circular motion. Do you hear the difference there? It's night and day. We moved from a simple, isolated fact to a robust chain of cause and effect. Don't just tell the examiner what happens. Tell them exactly why and how it happens using the correct terminology. That is how you unlock the highest mark bands. Now, part of successfully translating the physics heavily involves visual data. When you're analyzing orbital relationships on the paper, you are almost certainly going to encounter graphs. And let me be clear, you cannot just glance at a graph, guess the general trend, and move on. You have to physically interpret the mathematical elements. First up, the slope meaning. What does the gradient actually represent in the real world? If you're looking at a distance time graph of an object in orbit, the slope is the orbital speed. Second, the area meaning. If you're looking at a speed time graph, the area under that curve isn't just empty space. It represents the total distance traveled along that orbital path. Third, and this is absolutely crucial for orbits, the direction meaning. We're dealing with vector quantities like velocity here. In an orbit, a change in direction means a change in velocity, which means acceleration is occurring, even if the actual speed remains constant. That is a classic trick question for circular orbits, and they love putting it on the paper. Finally, the shape meaning. Is the curve linear, or is it an inverse square curve representing the weakening of gravity over distance? You must always translate the visual geometry of the graph into real physical quantities. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's keep this momentum going. Let's move to Section 4, Real-Life Applications. This is where we take the physics outside of the classroom. Remember earlier when I said Cambridge doesn't test physics in a vacuum? They really want to know that you understand how these invisible forces shape the tangible world around us. You are frequently going to see exam questions wrapped up in scenarios about modern technology or new astronomical discoveries. Think about engineering and safety. We have to calculate the exact trajectory required so a brand new satellite doesn't collide with thousands of pieces of existing orbital debris. Think about transport systems. Our entire global shipping and aviation network relies heavily on GPS satellites sitting in medium Earth orbit. Communications. Geostationary satellites are the reason you can stream videos or make international calls without a second of lag, because they stay perfectly fixed over one point on the Earth. Even medical technology relies on spin-off engineering from space exploration. And of course, astronomy. We use these laws to predict the paths of comets or even calculate the mass of distant stars based on planetary orbits. I want to challenge you right now as a sort of interactive workshop. Imagine a 60-second timer on your screen. Pick one of these fields. Can you name a specific situation where understanding orbital physics directly improves outcomes? Because a top candidate can always name a real-world situation and explicitly explain why the physics helps us predict the outcome. Section 5. The exam lens. Let's start spotting common exam weaknesses like a real Cambridge examiner. So we really need to evaluate how safe your answering methods are. Let's look at the most common weaknesses that just drain marks away and the safest methods to fix them. First weakness, writing a naked formula. Listen, just writing v equals 2 pi r over t gets you absolutely nowhere if the command word asks for an explanation. The safest method here, state the formula, yes, but explain the variables. Tell the examiner explicitly that v is orbital speed, r is the orbital radius, and t is the time period. Second weakness, simply quoting a process. This looks like a student just saying, the satellite stays up. That's not physics. The safest method is to link to a physical effect. You need to explain that the satellite is continuously falling towards the Earth due to gravity, but because of its extremely high tangential forward speed, the Earth's surface essentially curves away beneath it at the exact same rate it falls. Finally, the third weakness, giving an example without context. That's a very weak link. The safest method is to show why it follows physics. If you decide to mention a geostationary satellite, prove you actually know why it works by stating that its orbital period perfectly matches the Earth's rotation of 24 hours. That's how you lock in the marks. Let's actually do a quick speed round here, a find the flaw exercise, to really test your exam lens. Imagine a question on the paper asks, explain how a satellite maintains a stable circular orbit. And a student, maybe a bit panicked, like our friend Sam, writes only this, F equals mv squared over r, gravity makes it orbit. I want you to take a few seconds. Look at that answer. Can you spot the massive flaws based on the weaknesses we literally just discussed? Okay, first off, they dropped a naked formula. They didn't define mass, they didn't define velocity, they didn't define radius. Second, they quoted a process, gravity makes it orbit, without establishing any sort of cause and effect chain. They completely failed to explain that the gravitational force provides the centripetal force, acting towards the center of the orbit, which is what constantly changes the direction of the satellite's velocity while keeping its actual speed constant. That simple, flawed answer might get, 1 mark out of 4 if the examiner is feeling generous? But by applying our safe methods and that 4-step PO blueprint, you easily, effortlessly sweep up all 4 marks. Section 6. Final memory prompts. These are your ultimate recall triggers. Look, everything we have discussed today, the PL blueprint, the strict physics translation, looking through the examiner's lens, it is all completely useless if you forget it the moment you walk into that cold exam hall. So, here are the 4 critical revision prompts you absolutely must use for the topic of objects in orbit. Every single time you review this chapter, I want you to ask yourself these questions aloud. Prompt 1. What is the core idea? Answer. Circular motion requires a resultant centripetal force, and in space, that is provided by gravity. Prompt 2. What changes physically? Answer. The direction of velocity is constantly changing, meaning the object is continuously accelerating toward the center, even if the speed is steady. Prompt 3. What quantity or graph shows it? Answer. The formula v equals 2 pi r divided by t, or perhaps a graph showing gravitational force decreasing as the square of the distance increases. Prompt 4. Where is it used? Answer. In deploying GPS, weather satellites, and understanding planetary systems. If you can answer those 4 prompts aloud, clearly and confidently without checking your notes, your knowledge on this topic is rock solid and secure. I want you to think about the number 2 right now. This number represents the average improvement in grade boundaries for students who actually implement these precise physics strategies. Think about that. When students finally stop giving raw, unstructured fact dumps and start utilizing the 4-step Peel blueprint and cause and effect chains, they see a massive leap. We are literally talking about the difference between a C and an A, or bumping a B up to an A star. But here's the catch. This transformation only happens if they practice consistently with these structured techniques. It's not magic. It's about working smarter, decoding the command words, and deeply understanding the mechanics of the exam itself. So, here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by without having this incredible blueprint in your toolkit. To wrap up today's explainer, I want to leave you with this final thought and challenge. Drop a comment below with your target grade for physics and the biggest challenge you're facing with objects in orbit right now. Seriously, is it the math? Is it visualizing those invisible forces? Let us know. Our team responds to every comment, and your specific hurdle might just be the topic of our next video. Like and share this video with a study partner who really needs to see their completed paper before they start. Keep practicing that 4-step blueprint, ace the exams. Your Cambridge success starts here.